Now we talked a little bit about the case where we have a pendulum hanging and some object hits it. Okay, that problem as stated on the test, and a couple of people got that problem, wasn't fully stated. We didn't have enough information. You would have had to make some assumptions. So if you didn't make those assumptions, or if you made assumptions and did get it right, I simply dismissed the problem. I omitted it from consideration. But the idea is, for example, if you have an inelastic collision, you know that the two masses stick together, so you can easily figure out how fast they'll be moving immediately after the collision, and that will lead you to a calculation of the centripetal acceleration, the centripetal force necessary to hold the masses on the pendulum, and to conclusions about the tension in the pendulum. If the collision is elastic, and this is where all this comes from, if the collision is elastic, then what? Then we know that two things are so. We know that the total momentum before equals the total momentum after, so that the m1 v1 plus m2 v2, where v1 and v2 are the velocities of masses m1 and m2, before collisions equal to m1 u1 plus m2 u2, the products of mass and velocity, sum of the products of masses and velocities after the collision. That's one statement. Another statement is that the change in momentum of the first object is equal to and opposite to the change in momentum of the second, which is much closer to the statement of the impulse momentum theorem and the application of that theorem. Since the F delta T of one object on the other is equal and opposite to the F delta T of that object on the first, you have equal and opposite impulses giving you equal and opposite momentum changes. And this is a direct result of that. Or you could say that m1 times delta v1 plus m2 delta v2 equals 0. In other words, the change in the momentum of the first mass, which is the mass times its change in velocity, plus the change mass times change in velocity of the second, has to equal 0 because the forces being equal and opposite, the impulses are equal and opposite, the changes in momentum are equal and opposite, so the total change in momentum is 0. That's another expression of the conservation of momentum for an isolated system of two objects. Okay, well, we could have any of these three statements, any of these three, they're all equivalent, and each can be rearranged to give you the other. Each can be algebraically rearranged very easily to give either of the others. Okay, now the other condition, though, if the collision is elastic, then kinetic energy is conserved. That's what it means for the collision to be elastic. Now, one way to express that is that 1/2 m1 v1 squared plus 1/2 m2 v2 squared, the kinetic energy of the first plus the kinetic energy of the second before collision, is equal to 1/2 m1 u1 squared plus 1/2 m2 u2 squared, the sum of the two kinetic energies after collision. That's conservation of kinetic energy. Now, through the magic of algebra, you can take this statement and this statement and reduce them to any one of these three statements and just this statement, the statement that the relative velocity of the two objects reverses. What's that mean? The relative velocity of, and I think I have an error there. Let me fix that. Never mind. I thought I'd made a mistake and I hadn't. Just looked at it cross-eyed. The relative velocity before collision is, we can express that as v2 minus v1, the velocity of the second minus the velocity of the first. And the relative velocity after collision would be u2 minus u1, the velocity after collision of the second minus the velocity of the first after collision. Now, this will have to equal the negative of this. And all this simply means, if you think about it, is if I'm in an elastic collision, I see the other object coming at me with this kind of velocity. Okay? After collision, I see the other object receding from me just as fast. So if I see that object coming at me at 10 meters per second, after the collision, I'll see it receding from me at 10 meters per second from the perspective of my frame of reference. And that's all this is saying. And that is a condition that ensures the conservation of kinetic energy. This then gives me two equations that I can use to analyze any situation. So for example, if I know the two masses and let's say the before collision velocities, then the only thing I don't know in this equation is the two after collision velocities. And also the only thing I don't know in this equation is the two after collision velocities. So I've got two equations here that I can solve for U1 and U2. And if I know any two of the, if I know the two masses and any two of the velocities, then I know two of the four velocities. And when I say any two of the velocities, I mean the before or after collision velocity of one object and the before or after collision of maybe the other object, or the after collision, well, you can think about the combinations. Any two of the quantities V1, V2, U1, and U2 allows me to determine the other two if I know the two masses, because I have the information in the simultaneous equations. Of the quantities M1, V1, M2, V2, U1, and U2, there are six quantities there, six quantities. As long as I know four of them, I can find the other two, whatever the four I know, because I'll have two simultaneous equations with only two unknown quantities. That's how we can analyze an elastic collision.